Okay, so in this video, I'm going to demonstrate how to use the orthogonal fractional contrast codes that we've created in the previous videos and how we would run those. Um, so let's go ahead and do that. So this, again, is the first analysis we ran for our data, where we compared the four different groups we have on the dependent variable. And we ran this kind of traditional ANOVA. So I'm going to demonstrate now how we can use the contrast codes that we created to test our specific hypothesis. So if you remember, in scenario one, we created this set of contrast codes, but really the whole purpose was that we wanted to make sure we tested our primary hypothesis, which was that uh, Group 4 will have significantly higher scores on the DV compared to the other three groups. Okay, so let's go ahead and run this set of contrast codes in jamovi. So let me show you how to do that. So we would go to Analyses, and you could use a couple different ways. I really prefer this General Linear Models module. I find this very, very powerful. But just in case you don't have that yet, we're going to go ahead and use regression for now. So you can use the regression module, and you could use linear regression. Okay. So here we're just going to put the dv in the dependent variables box. Okay. And then we are going to take the three codes that represent our first set of orthogonal fractional contrast codes. These are the three codes. We could just kind of confirm by going back. These are the variable names. So, okay, yes, these are the same. And what we're going to do is we're going to put them into the covariates box in jamovi. Okay. Um, let's ask for a couple more things. So for assumptions checks, I want to get the co-linearity statistics. And then under model fit, let's go ahead and ask for the F-test. And then for model coefficients, let's ask for ANOVA, maybe the confidence interval, and the standardized estimate. Okay. So what you should see here is this looks like linear regression because it is. ANOVA is just a part of the general linear model, so it's just a very specific case of it. So what we've done here is we've created orthogonal fractional contrast codes to address our question of interest. So first off, let's just double check a couple things. So I told you earlier in a couple of the other earlier videos that what we're going to do here is statistically equivalent to running that one-way ANOVA that we did before. So let's just quickly demonstrate that. So if you look here, we see this omnibus test. The F is 3.866, the p-value is 0.031, and this partial eta squared is 0.139, and the degrees of freedom for this test is a 3. So let's go down and just look to see if we could find that information on our regression output. And indeed we can. So it's right here in this overall model test. So there's our 3 degrees of freedom. There's that p-value of 0.013. Here's the f of 3.866. And then that r squared, that 0.139, matches our partial eta squared. So those are actually equivalent. For these purposes, these are equivalent effect sizes. So that should demonstrate to you that what we're doing here is actually statistically equivalent to what we were doing with the one-way ANOVA. But if we scroll down, when we use these orthogonal fractional contrast codes, we can see that this first code, again, this is testing our primary hypothesis, comparing group 4 to the combination of the other three groups. We can look down and see, okay, that is actually statistically significant. So that is consistent with our hypothesis. So remember, one of the limitations of this approach is this is statistically significant, less than 0.05, that's your alpha level, but it doesn't tell us a whole lot. All it can say is that there are mean differences somewhere. And then if we just kind of use the post hoc tests that are in here, like given to you in jamovi, the way we would test our hypothesis is actually kind of clunky. We would have to compare, we do 3 separate post hoc tests comparing group 4 to group 1, group 4 to group 2, group 4 to group 3. So it's not very elegant or concise way to test our hypothesis, which is group 4 different from the other 3 groups? So what we can do instead is create these orthogonal contrast codes. And again, right off the bat, there's no like running post hoc tests, a bunch of different tests. We run a single test and we see we don't even actually care about this omnibus test. This isn't our research question. This is. So this would be the first thing we look at. We're not running a whole bunch of different tests to test our hypothesis. We're running one test. And we see that it's consistent with our hypothesis, that group 4 is significantly greater than the other 4 groups. To just get a clear sense that that's actually what's going on, we could just look at this graph that we generated before. Group 4 is way up here, and then the other 3 groups are down here. Okay. And one of the reasons, again, why we wanted to make sure that we made them fractional is because I said the parameter estimate we get from the regression analysis will give us the mean difference. So that's what this ends up being. You could do the math yourself to demonstrate this, but what this value right here is actually telling us is that group 4's mean on the DV is 2.825 points higher than the mean of the other 3 groups on the DV. Okay, so that's very convenient. What are the other codes telling us? So this code, not our primary hypothesis, but this question's being tested comparing group 3 to the mean of the other 2 groups combined. We see that that's not significant. The third code is comparing group 2 to group 1. That's also not statistically significantly different. Okay, so this is good. So hopefully you're seeing some of the utility of using this approach. It's a sleeker, kind of quicker way to test our specific hypothesis. And then finally, just to demonstrate, what we've been saying this whole time in this series of videos is we want our codes to be orthogonal. And what I mean by that is we don't want our codes to be correlated with each other. And one way to just check that is with the co-linearity statistics down here. So what this is telling us, these tolerance values of 1, is that each of these codes is 100% tolerant of the other, meaning they're not related at all. So that if you were to create a correlation, Pearson correlation of these 2 codes, any pair, or any of these codes, I should say, they won't be correlated with each other at all. Okay, so that was on purpose. That's why we went through all those steps in the previous videos to make sure they're orthogonal, and this is just demonstrating to you that they are completely tolerant of each other. Okay, so there's 0 multicollinearity here. And the reason why it's a perfect 1 on the tolerance is because we have an equal number of participants in each group. Whereas if one group had more or a few less, this tolerance wouldn't, I don't believe it would be perfectly 1, but it would be like 0.99999, which is a very, very good tolerance level. Okay, so I'm actually going to just record a separate video for scenario 2. So that is scenario 1.